This is perhaps podcast number 72, and today we're looking at the aerodynamics of the Hyperloop. So, if you haven't heard, the Hyperloop is the underground train that Elon Musk is making between various cities, for example, LA and San Francisco. The idea is that you bore out a tube underneath, a tunnel underneath, then you make it effectively a vacuum, so you suck out all the air, and then you send this like pod all the way through at very high speeds. And because there is very little air in the tube, you can reach much higher speeds without incurring the drag penalty that you would with like a train, for example. So we're looking at the aerodynamics of that today, how the pod itself and also relative to the tunnel itself, how that affects the drag. So we're going to look at different parameters. And just a heads up, we're going to make this two podcasts because this covers a lot of details about the Hyperloop idea. It's going to be a good couple podcast episodes. So to look at this idea and these aerodynamics, we're going to look at a paper called Numerical Analysis of Aerodynamic Characteristics of Hyperloop System. And this is open access, so you can find it in the link in the description. So they start off with high-speed trains, which are typically what we've had for quite a number of years, actually. And they mentioned later that the Germans back in 1936 patented, I don't know which Germans, but a couple of Germans patented the idea of high-speed trains based on magnetic levitation. And obviously that's the general principle that most high-speed trains do use these days, as far as I'm aware. And so let's start off with the high-speed train. So the high-speed tube train has many advantages over conventional railways and aviation in terms of speed, energy efficiency, and stability, reducing both environmental and operating costs. Construction costs remain significant, but can be further reduced by using the optimal cross-sectional design. So high-speed train technology has been widely researched. In Japan, the research and development of high-speed magnetic levitation railways, enabling travel speeds of up to 500 kilometers per hour, occurred in the 1970s. And in 2007, the JR Central announced the establishment of a practical high-speed magnetic levitation railway line. So JR is I don't know if it's government owned or whether it's privately owned, but that's the main company that does high-speed trains in Japan. And you can take a high-speed train from Tokyo to the up north, like to the top of the main island in like less than 3 hours. We get there. It's quite a long distance. So at present, the maximum speed recorded along the Yamanashi high-speed maglev train test line is 581 kilometers per hour, which is very high considering how dense the air is at ground level. So Elon Musk, let's move on to the Hyperloop idea now. Elon Musk presented a new high-speed tube train concept called the Hyperloop in 2013. In the Hyperloop system, a pod travels in a confined tube at transonic speeds. So transonic means when you're reaching the speed of sound. And this is a really cool concept because back in like the 1950s, when they were really trying to break the speed of sound, it was seemed to be impossible to break. And the reason why is because as it kept getting closer to the speed of sound, so we denote something called the Mach number. The Mach number tells us how close we are to the speed of sound. The Mach number of 1 equals that you are at the speed of sound. Below that is you're below, above that you're above that. So when they were like, let's say, a Mach number of 0.8, they found that the drag that they were experiencing, so the resistive force to their object that they were traveling in, just started to increase, and they increased the speed more to Mach 0.9. It went up even more, and it just kept going up and up and up. And it seemed like it would get to a point where the drag would just be an infinite number, so you could actually overcome that drag and break the sound barrier. So, but they finally found that the best way to do that is by a clever design, and the way to do that is you make the front of your object sharp, and you make it quite slender, and you don't make any sudden changes in the cross-sectional area. All these things that you do will make it easier to meet the sound barrier, to meet the speed of sound, and break the sound barrier. And so finally they broke it in the 50s or so. Anyway, so the transonic speeds are very difficult to operate under because there are such great resistive forces. To get over that, they say a near vacuum state of around 100 pascals, which compared to atmospheric pressure. Atmospheric pressure is 101,000 pascals approximately, so this is 1,000 times less. So this vacuum state is created in a confined tube, thus drastically reducing the air resistance on the traveling pod because the density of air is reduced. And as we know, the drag is dependent on among other things, the density of air. So by reducing that, you can reduce the drag. So the target speed of the Hyperloop is 1,250 kilometers per hour, which is 1.5 times that of commercial airlines or commercial airplanes. If this target is achieved, the 650 kilometer from San Francisco to LA could be covered in approximately 30 minutes. In designing of a Hyperloop system, aerodynamic limitations such as drag become critical issues. Drag is one of the most important parameters in the analysis of objects moving at very high speed, especially within confined tubes. Lower drag in a Hyperloop system that not only drastically reduces construction and operational costs, but also minimizes the energy load of propulsion system. So the less drag you have, the less energy you need to give it to continually go at that speed. In other words, drag reduces the overall performance of the system, further complicating aerodynamic physics of the Hyperloop system. There are two main conditions that cause drag. In this particular case, I should mention. So first is the occurrence of choked flow, in which the Mach number reaches its critical level, and the second is the presence of shock waves, which are observed at supersonic speeds. So let me just explain the idea of the critical level of the Mach number, so also known as the critical Mach number. So this critical Mach number is the point at which the free stream flow will become sonic over the object. Sonic means it reaches the speed of sound. So you might think, well, wouldn't that just be when the free stream velocity is the speed of sound? But it's not actually, it's lower than that. And the reason why is because if you think of, let's say, an airfoil, if you've ever studied airfoils, you know that over the top of an airfoil, the flow accelerates. And that's because it's a slightly curved surface or however curved it is. So even though you might have a free stream velocity of, let's say, a Mach number of 0.9, because the flow has to accelerate over the surface of the airfoil, it will hit 1. And that's when you get sonic flow. So that means the critical Mach number is actually 0.9 because that's the free stream velocity at which you'll start getting sonic flow over your object. So that's what they mean here by this critical level for the Mach number. So moving on, they say that the Hyperloop Alpha proposed two methods to significantly to delay the significant increases in drag caused by choke flow and shock waves. First, they increased the blockage ratio, which is the ratio between the cross-sectional area of the tube and the cross-sectional of the pod. I should mention that I think this is a typo. They should actually mean decreasing the blockage ratio. And the reason why I think that is for two reasons. One, it makes sense because if you decrease the blockage ratio, it means the pod isn't taking up as much of the volume or the cross-sectional area in the tube. But they also say this method introduces a relatively large amount of air between the tube and the pod, decreasing the flow velocity around the train so that the flow phenomenon such as choked flow and shock waves do not occur frequently. So this means that if you reduce the blockage ratio, the flow doesn't have to accelerate as much around the train, which means that the critical Mach number increases. So that means instead of it being Mach number of 0.9, it might be Mach number of 0.95. So you can go slightly faster without getting sonic flow over the object, which means that your choked flow will also reduce and also you won't have as many shock waves. So secondly, the second way to reduce drag is a similar effect was achieved by installing the compressor on the front of the pod. So that's quite interesting. So let's talk about the aerodynamics on the pod. A compression wave generated by the entrance of a train into a tunnel propagates along the tunnel in the opposite portal. This phenomenon is unique to railway systems in which the pod speeds are sufficiently high to create a significant compression wave, and in which the tunnel is sufficiently long for this compression wave to develop into a pressure discontinuity. So that's pretty cool. This pressure wave travels down the tunnel and forms a pressure discontinuity. So that means you have a disconnect between the pressure ahead of the wave compared to behind the wave, because the wave is obviously compressing the flow. So that makes sense. So the effects of different factors on the drag of a high-speed capsule were studied by a few researchers who reported that different operating speeds and working vacuum pressures significantly affect the drag of the capsule. The investigation of the head and end shape of the train with respect to drag was also found that lower drag occurred when particular shapes were used, which makes sense. And I'm guessing that they're probably going to be sharper shapes instead of like a blunt object, a bluff body. Previous studies have not fully investigated the influence of the primary design or operating conditions, so the blockage ratio, pod length compared to the speed, and tube pressure compared to the temperature on drag. Hence, this study focuses on the influence of the above factors over a large parameter space. So in other words, they're going to be looking at the drag that's being developed at different blockage ratios, different pod lengths, different speeds, different pod lengths, two speeds, different tube pressures, different temperatures, different tube pressures compared to different temperatures. And this is important because air is effectively an ideal gas. It's very close to it, which means that the pressure and temperature are very closely related. And if you change one, the other one will change. So it's interesting to note how changing these ones will affect the drag. That's what we're going to be looking at in this these next two podcasts. So in this study, a viscous and compressible steady state flow model was employed and smooth tube and pod surfaces were assumed. So what this means is the Mach number is above 0.3, which is the approximate rule of thumb that we say above that, the flow is compressible, which means that the density of air can change. Below that, we assume that density of air doesn't change with respect to velocity. However, it does to some extent. Once you reach Mach number of 0.3, it's about a 2% compression that you'll get. But we assume that that's okay. We can live with that, but depends what your requirements are. So the isentropic definition of the speed of sound is the speed of sound equals the square root of gamma times r times t. So gamma is the ratio of the specific heats. So specific heats are at different. The specific heat is the amount of energy you need to raise the temperature of a gas, in this case air, by 1 degree Kelvin. So, and this is under different conditions. So whether it's under the constant volume or constant pressure. So the ratio of these two numbers gives you gamma. And we'll talk about that a little bit later. R is the gas constant, and this changes depending on the gas. So for air, it's approximately 287 joules per kilogram Kelvin. And T is the temperature in Kelvin. So if you times gamma, the ratio of specific heats, which is usually 1.4, and that's based on effectively the chemistry of air. R, which is 287, and temperature, which is whatever temperature you have, and then you square root that, you'll get the speed of sound. So the pod speed at the inlet that they're going to be looking at was set anywhere between 25 meters per second and 350 meters per second. There are a whole bunch of ones they're looking at. And this corresponds to a Mach number of 0.07 up to 1.01. So just above the speed of sound. The pressure at the inlet was set anywhere from atmospheric pressure, so 101,000, all the way down to 250 pascals. And then the temperature was set between 275 Kelvin, which is 2 degrees Celsius. So I guess that would be about 28 degrees Fahrenheit, to 325 Kelvin, which is like a really hot day, 42 degrees Celsius, which is like 125 degrees Fahrenheit or so. So pretty toasty. In this study, the Reynolds number was, this is interesting here. So the Reynolds number we calculate usually based on the characteristic length, but here they say the Reynolds number was calculated for the blockage ratio, tube pressure, and pod speed. The Reynolds number, by definition, is calculated using the parameters density, viscosity, velocity, and the characteristic length, which are the tube background density, viscosity, specific pod speed, and hydraulic diameter. So they're using the hydraulic diameter, which is effectively the difference between the how much area there is available once you take out the area that the pod is taking up, if that makes sense. So in other words, as you change the blockage ratio, the hydraulic diameter changes. So this is how they're defining the Reynolds number, which is okay to do. It's fine. It's just not very common that we see it this way. We often see it just as like a simple characteristic length. So I thought this was quite interesting. So what they say is as the flow and tube pressure increase, the Reynolds number increases. In case of high Reynolds numbers, transition and separation phenomena occur, and such phenomena also occur in case of low Reynolds numbers at the downstream section of the pod. So figure 1, let's scroll down here, shows the trend of the Reynolds number along with the pressure changes at two different blockage ratios. So the blockage ratios were 0.25 and 0.35. And the Reynolds numbers here range from 6,300 to 930,000. So what we find here is as the speed of the pod increases, regardless of the pressure that they've sucked, like they've kept in the tube, the Reynolds number increases and is fairly non-linear, sorry. And interestingly, even though they're reaching speeds of about 350 meters per second, which is above Mach number 1, the Reynolds number doesn't really reach above 1 million. So this is quite an interesting thing to talk about. So why is that? Because the density is so low. Even though the velocity is really high, then the characteristic length is decent. It's not very small. It's not like a little acorn or something. It's actually like a big train. The density is so low that the Reynolds number is very low. So that means that you could still be operating in a transitional regime or even a laminar regime because the Reynolds number is so low and there may not be many disturbances. So that means that you can potentially reduce the skin friction drag because the velocity of the flow near the surface is going to be very low compared to if you had a turbulent boundary layer. So that was quite interesting. So let's move on to some results. The 5 main design parameters of the Hyperloop system are the blockage ratio, the pod speed and length, and the tube pressure and temperature. To enable a comprehensive analysis of the drag on the pod, so they did some simulations over these different parameters ranging from like different values from very low to moderately high, depending on what the parameters were. And they looked first at the effects of the blockage ratio and the pod speed. So the critical Mach number is the speed at which the choked flow occurs. So when the flow reaches sonic, anywhere along the object. Choked flow means that it's I guess a somewhat difficult idea to think about conceptually. It's just where the flow has difficulty flowing. So it reaches this point where it all gets crammed into, and then ahead of this flow, now there's kind of like this discontinuity where there isn't really any flow or a very small amount of flow, and behind it there's a huge amount of flow being crammed together, and that's because air cannot travel faster than the speed of sound. So if you reach that, you're then going to get it to a point where you have to somehow get past that to then you get supersonic. So there's that discontinuity there, and that's what caused the problems with reaching the speed of sound back in the 1950s. And I remember then the guy's name, I think, who broke the sound barrier was called Chuck Yeager. And there's a book about it called The Right Stuff, and it's pretty good. I haven't read it, but I have a friend who read it, which is almost as good, really. Let's face it. And he raved about it, so I'm guessing he's pretty smart. So I'm guessing it's a good book. And there's this quote from it called "Spam in a Can" or something. So it sounds good. You should read it, and then tell me how good it is, so I don't have to read it. Okay, let's move on. When the Mach number is locally greater than 1, a shockwave can appear, leading to a rapid increase in drag, as seen in Figure 4. So Figure 4 doesn't really show us too much. This phenomenon of the Hyperloop system is similar to converging diverging nozzles. So converging diverging nozzles are a way that we generate sonic flow. What we do is, or supersonic flow even, what we do is we have a nozzle at the front, it has a very large cross-sectional area. So that means that when you put flow through it, it then reduces in cross-sectional area and the flow has to accelerate. And at the point of the smallest cross-sectional area, ideally the flow will be at the speed of sound. Then when you diverge the nozzle, the flow will then accelerate past the speed of sound. That's in theory. Now there's a whole bunch of different conditions the way it could cause changes to this. So it may not operate in this way, but this is ideally what you'd want to do in this particular case, converging diverging nozzles. Interestingly, once you get above the speed of sound, if you diverge the nozzle, then it can actually reduce the velocity under certain conditions. So that's getting into some quite complex physics. So in this study, the critical Mach number is calculated using the assumptions stated above. In the Hyperloop system, the critical Mach number varies with the blockage ratio according to a certain formula. And this is a really cool formula because literally it only relies on the blockage ratio, the Mach number, and the specific heat constant, as I mentioned earlier. The specific heat ratio. The specific heat ratio is the ratio between the specific heats of gas, whatever you're using, so air, at a constant pressure and constant volume. And in this particular case for air, it's 1.4. So based on literally 4 parameters, the area, cross-section area of the tube, cross-section area of the bypass, so the rest of it, the Mach number, and the specific heat ratio, you can calculate what the Mach number is, what velocity that is. So the blockage values used in this case study were 0.25 and 0.36, corresponding to critical Mach numbers of 0.5 and 0.41, respectively. So in other words, as the blockage ratio goes down, the critical Mach number increases. Hence, the blockage ratio is inversely proportional to the critical Mach number. Equation 10, which we just mentioned above, where it was reliant on the specific heat ratio, Mach number, and the blockage ratio, however, was based on one-dimensional isentropic assumptions. The present CFD has a two-dimensional effect, which made the critical Mach number of the present study higher than that of a one-dimensional study. So two-dimensional effects change the speed of sound, which is pretty cool. Figure 5 shows the effects of the blockage ratio on the drag. Let's look at figure 5 now. Let's scroll back up. So figure 5a shows that the change in the total drag, pressure drag, and friction drag with respect to the blockage ratio. So the total drag in this particular case is equal to the pressure drag plus the friction drag. In other applications, you may have other components of drag, but in this particular case, we really just have two components of drag, pressure drag and friction drag. Pressure drag is what it sounds like. It's the drag caused based on the pressure difference across the surface. So if, let's say, you have your hand and you're waving it through the air, the part of your hand which is upstream, that's going to experience a higher pressure because there's all this air just like being pushed into it. The face of your hand that's trailing along, that's going to experience a lower pressure because there's not any air that's crashing into. So there's a pressure difference between that across that surface. That's going to result in a pressure drag. Friction drag is exactly what it sounds like too. So friction arising from flow going over a surface, and that's creating drag. So the changes in drag exhibited a similar tendency. First, as the blockage ratio increased, the influence of the drag on the pod increased. As the speed increased, the drag increased. Second, when the blockage ratio was 0.36, there was a significant increase at 200 meters per second near the end of the pod. So we can see that, as I mentioned, regardless of the blockage ratio, when you reach about 250 meters per second, there's a change in the drag significantly. So it goes from being like kind of an exponential sort of curve looking to more a linear type of curve now. So that's interesting. Now, the third, we can confirm that the slope of the drag decreased above 250 meters per second, as I mentioned. This phenomenon was related to the results in figure 5b, which showed that the ratio of the total drag to the pressure drag. So below 250 meters per second, the pressure drag started constituting more and more of the overall drag. And that makes sense because as you go faster, the friction drag will increase a little bit because the velocity on the surface is increasing, but the pressure drag is going to be increasing a lot more because you're reaching the critical Mach number. So you're getting this greater pressure difference between the front and back of your object. However, once you get to 250 meters per second, regardless of the blockage ratio, the component of drag that the pressure drag makes up plateaued. And so that equaled 92.5% of the entire drag was pressure drag, and that did not change from 250 meters per second to 350 meters per second. So for some reason, there was an entire range there from effectively a Mach number of 0.66 or so, maybe 0.7, to Mach number of 1, where this component of drag did not comprise any more of the total drag. It did not increase, as you might expect. So as the pod speed increased, the pressure drag increased proportionally with a larger blockage ratio enhancing the influence of the pressure drag. And the reason why that is because if you have a bigger pod taking up more of the area in the tube, it means that the flow has to travel faster around the pod just to get past, because if you have continuity, the continuity equation means that if you keep the density the same, you drop the area, the velocity has to increase because the density times the area times the velocity at one location has to equal the density times the area times the velocity at another location. So there's a relationship there. And because we have a higher blockage ratio, the area that is available for the air to go through drops, so the velocity has to increase. So beyond the critical Mach number, the choking phenomenon was very severe, meaning that the differences in the blockage ratio did not have a significant effect on the ratio on the pressure drag to the total drag. So that's why we saw that plateau in the pressure drag before. So let's talk about the effect of the pod length now. So we found that as you increase the blockage ratio, you're going to be increasing the drag. Also, if you increase the speed, that the drag dramatically increases up until a point, and then it sort of plateaus off a little bit. Now let's look at the pod length. So previous studies only investigated the pod lengths less than 43 meters. However, this would restrict the pods to transport a maximum of 28 passengers at a time. So the Hyperloop Alpha document suggests that with 28 passengers at approximately 2-minute intervals, the Hyperloop could transport 840 passengers per hour to the destination. However, this condition is very energy inefficient and presents a high risk of accidents. Therefore, it is necessary to increase the pod length and investigate the effect of the length on the drag. In this study, the pod length was set to 10.75 meters all the way up to 86 meters, so double the 43 meters, which means that you could have, I guess, twice as many passengers or so. And the change in drag was analyzed. So figure 6 shows the change in drag with respect to the pod length. And figure 5b and 6a confirm that the total drag and pressure drag are almost insensitive to the pod length, which makes sense. So the reason why is because the amount that the flow is going to have to accelerate is really just based on the blockage ratio, not the length of the pod. There might be some small changes because you have viscosity playing effect, which then reduces the velocity and that. But overall, there's going to be fairly independent of the length of the pod. And it's really only dependent on the front pressure compared to the back pressure, because the rest of the pod is really the surface is in the parallel direction to the free stream velocity. And as you increase the speed of the pod, regardless of the length of it, the total drag increases dramatically, and then it sort of plateaus off again, as we saw once you hit 250 meters per second. That's because the pressure drag seems to be increasing linearly instead of exponentially. So, coming back, they say, however, the friction drag is proportional to the pod length, which makes sense. If you have a greater surface area, you're going to have more friction. As the influence of the pressure drag does not change, the ratio of the total drag to the pressure drag decreases. So in other words, the total drag increases more than the pressure drag increases, and that's because the friction drag also increases, so it makes up even more drag. So as the influence of, I mentioned that before, and they mentioned because the friction drag is taking up, is comprising more of the total drag as you increase the pod length. As a result, changes in the pod length do not significantly affect the drag, as most of the drag is caused by the pressure. So increasing the pod length means you can transport more people. You'll get a slight increase in the drag, but not nearly as much if you were to change other parameters, mainly because the main component of drag is the pressure drag, and the small changes in the friction drag, the small increases, don't really comprise too much of a don't really result in too much of an increase in the total drag because it's so small to begin with. So that's where I'm going to end this podcast, and we're going to pick up later talking about the rest of the parameters and other flow physics in the Hyperloop system. And so make sure to like, subscribe. And if you want to make your experiments better, so you're in aerodynamics and you're doing experiments, or you have your CFD and you need experimental data to validate your CFD, make sure to measure the density of the air in your system. We've talked about it in this paper, how the density of air can change, and it does change on a regular day by 2 to 4%. As I'm sure you're aware, we made a podcast about it, podcast number 54, and it shows how the changes in the density affect the flow physics and forces on bluff bodies and streamlined bodies. And we make an instrument called the Atmosphere Hawk that accurately measures the density of air for you, and it gets rid of that error, so it makes your life really easy, and it makes your experiments much more accurate, and it makes your CFD validation process much easier because now you're actually using your CFD with the same density as you have in your experiments. So that's what you need to do. If you don't do that, then you're going to be introducing errors, and it's going to be much harder to find good trends. So make sure to pick that up, link in the description, and I'll see you in the next podcast. Peace out, amigos.